Welcome to this comprehensive lecture on next-generation nanodevices. We're going to explore the fundamental nanoscience breakthroughs that are revolutionizing technology as of December 2025. Before we dive into the cutting-edge developments, let's establish what we mean by nanodevices. These are functional structures operating at the nanometer scale, typically between 1 and 100 nanometers. To put this in perspective, a DNA helix is about 2 nanometers wide. Typical proteins are 5 to 10 nanometers, and a human hair is roughly 80,000 nanometers wide. We're working at the scale of individual molecules. You might ask, why is this particular scale so special? At the nanoscale, quantum mechanical effects become dominant, and materials exhibit properties vastly different from their bulk counterparts. Quantum confinement effects change electronic properties. Surface-to-volume ratios skyrocket, making surface chemistry incredibly important. And we can engineer matter atom by atom. Let's discuss the first major breakthrough, quantum dot arrays with perfect coherence. As of 2025, we've achieved quantum dot arrays that maintain coherence for over 1 millisecond at room temperature. Here's a representation of a coherent quantum dot array. Each green circle represents a quantum dot, and the yellow lines represent quantum entanglement between neighboring dots. What is a quantum dot exactly? It's a semiconductor nanocrystal, typically 2 to 10 nanometers in diameter, that confines electrons in all 3 spatial dimensions. The energy levels are quantized according to the particle in a box model. E sub n equals n squared h squared divided by 8 meters L squared, where L is the size of the quantum dot. Let's do a quick back-of-the-envelope calculation. For a quantum dot with diameter 5 nanometers containing an electron, L equals 5 times 10 to the negative 9 meters. The electron mass is 9.1 times 10 to the negative 31 kilograms. Planck's constant is 6.63 times 10 to the negative 34 joule seconds. The ground state energy E sub 1 equals Planck's constant squared divided by 8 times the electron mass times L squared. This gives us approximately 2.4 times 10 to the negative 20 joules, or about 0.15 electron volts. This energy corresponds to infrared light emission. By changing the quantum dot size, we can tune the emission wavelength across the entire visible spectrum. The breakthrough in coherence time enables quantum computing at room temperature. Previously, quantum computers required cooling to near absolute zero. This represents a room temperature quantum processor with a 10 by 10 qubit array. Each quantum dot acts as a qubit, the fundamental unit of quantum information. Why does coherence time matter so much? Quantum algorithms require maintaining superposition states. Decoherence destroys quantum information, and longer coherence means more complex computations. The number of operations you can perform is approximately the coherence time divided by the gate operation time. With 1 millisecond coherence and 1 nanosecond gate times, we get approximately 1 million operations before decoherence, which is sufficient for many quantum algorithms. The second breakthrough involves DNA origami nanorobots. These are programmable nanoscale machines built entirely from DNA strands that can perform specific tasks inside living cells. Here's a schematic of a DNA nanorobot. The red spokes represent DNA double helices, arranged in a specific geometry. The blue circle is a receptor domain, and the yellow rectangle represents a cargo compartment that can carry drugs or other molecules. How does DNA origami work? We use a long, single-stranded DNA scaffold, typically 7,000 to 8,000 bases long, derived from a bacterial virus. We design hundreds of short staple strands, each about 32 bases long, that bind to specific regions of the scaffold, folding it into the desired 3D shape. The number of staples needed is approximately the scaffold length divided by 32 times 2, accounting for both strands of the double helix. For a 7,000 base scaffold, that's about 440 staple strands to design and synthesize. The 2025 breakthrough is that these nanorobots now incorporate autonomous logic gates. They can sense their environment, make decisions, and execute actions without external control. The architecture is like this. A sensor domain detects specific molecular markers. A logic gate processes this information using DNA strand displacement reactions, and an actuator domain releases therapeutic cargo or changes conformation. For example, a cancer-targeting nanorobot can detect tumor markers, verify it's not a healthy cell, and only then release chemotherapy drugs directly at the tumor site. This drastically reduces systemic toxicity, because the drug is only released where it's needed, not throughout the entire body like traditional chemotherapy. Let's calculate the targeting efficiency with a back-of-the-envelope estimate. Assume our nanorobot has 95% sensitivity in detecting cancer cells and 98% specificity in avoiding healthy cells. The true positive rate, delivering drugs to actual cancer cells while avoiding healthy cells, is 0.95 times 0.98, which equals 0.93 or 93%. This is orders of magnitude better than conventional chemotherapy, which affects all rapidly dividing cells indiscriminately. The third breakthrough is atomically precise manufacturing, or APM. We can now position individual atoms with sub-angstrom precision to build nanoscale devices atom by atom. Here's a representation of a scanning tunneling microscope, or STM, positioning an atom. The green dots represent a substrate surface, and the red circle shows an atom being manipulated by the STM tip. How precise are we talking? Current APM systems achieve positioning accuracy of plus or minus 0.02 nanometers, which is about 1/5 of an atomic radius. That's 0.02 nanometers, or 0.2 angstroms. For comparison, a hydrogen atom's Bohr radius is about 0.53 angstroms. We're literally controlling matter at the most fundamental level possible, placing atoms exactly where we want them. One revolutionary application is molecular electronics, where individual molecules function as transistors, diodes, and other circuit elements. This is a single molecule transistor. The yellow rectangles are gold electrodes, the blue lines represent the molecular wire, and the red circle is the active switching molecule. Traditional silicon transistors are reaching fundamental limits. We're approaching the point where quantum tunneling and other effects make further miniaturization impossible. The practical limit for silicon transistor gate length is about 5 nanometers. Molecular transistors are just 1 to 2 nanometers, allowing much higher density. How much denser can we go? Let's calculate the theoretical maximum transistor density. If each molecular transistor occupies 2 nanometers squared, that's 4 times 10 to the negative 18 square meters. The density is 1 divided by that area, giving 2.5 times 10 to the 17 transistors per square meter. On a 1 square centimeter chip, that's 2.5 times 10 to the 13, or 25 trillion transistors. That's roughly 1,000 times denser than current chips. The fourth breakthrough involves metamaterial nanostructures. These are artificially engineered materials with properties not found in nature, achieved through nanoscale structure rather than chemical composition. This shows a metamaterial structure with periodic nanoscale features. The blue squares and yellow circles represent metallic resonators arranged in a precise pattern. When light interacts with this structure, it can exhibit negative refractive index. What does negative refractive index mean? In normal materials, light bends one way when entering from air. In negative index materials, light bends the opposite way. The refractive index n equals the speed of light c divided by the velocity in the medium versus. Normal materials have positive n, but metamaterials can have negative n, which seems to violate intuition but is perfectly allowed by Maxwell's equations. This enables perfect lenses that break the diffraction limit, and even cloaking devices that bend light around objects. In a cloaking device, the metamaterial shell bends incoming light rays around the object in the center, making it invisible to outside observers. The 2025 breakthrough is scalable fabrication of three-dimensional optical metamaterials that work across the entire visible spectrum. Previous versions only worked at single wavelengths or in narrow bands. Now we have broadband performance. Let's calculate what feature size we need for visible light metamaterials. Visible light wavelengths range from 400 to 700 nanometers. For effective interaction, feature sizes must be less than 1/10 the wavelength. That means features smaller than 40 nanometers, which is extremely challenging to fabricate in 3D. The fifth breakthrough is in energy harvesting nanodevices. These convert waste heat, vibrations, or ambient light into electricity at unprecedented efficiencies. This represents a thermoelectric nanomaterial. The red area is a temperature gradient. The blue dots are nanostructured features that scatter phonons but allow electron transport, converting heat directly to electricity. Thermoelectric efficiency depends on a dimensionless figure of merit called ZT. ZT equals S squared sigma T divided by kappa, where S is the Seebeck coefficient, sigma is electrical conductivity, T is temperature, and kappa is thermal conductivity. The fundamental challenge is that materials with high electrical conductivity usually also have high thermal conductivity, which reduces efficiency. Nanostructuring elegantly solves this problem. Nanoscale interfaces scatter phonons, which carry heat, much more effectively than electrons. Traditional thermoelectric materials have ZT around 1. 2025 nanostructured materials achieve ZT greater than 3, tripling the efficiency. What does this mean for energy conversion? Let's calculate the Carnot efficiency limit. The Carnot efficiency equals 1 minus T cold divided by T hot. For a 100 Kelvin temperature difference, say 300 K cold side and 400 K hot side, the Carnot limit is 25%. Actual thermoelectric efficiency is roughly 30% of Carnot, giving about 7.5% for ZT equals 3 materials. This enables self-powered sensors and Internet of Things devices that harvest energy from their environment, eliminating batteries. The sixth breakthrough is neuromorphic nanodevices that mimic biological neural networks. These are memristors and synaptic devices that can learn and adapt like neurons. This shows an artificial neural network implemented in hardware. Each blue circle is a neuron implemented as a nanoscale device, and the yellow connections are synapses with tunable weights. What is a memristor? It's the fourth fundamental circuit element, alongside resistors, capacitors, and inductors. It remembers its history. The voltage equals memristance M times current I, where memristance depends on the charge Q that is passed through. Memristance equals initial memristance plus a change that's a function of accumulated charge. This behavior mimics synaptic plasticity in the brain, where connection strengths change based on activity history. The advantage is massive parallelism and extreme energy efficiency. The human brain processes information using only about 20 watts. Let's compare with conventional computing in terms of energy per operation. A modern GPU uses about 10 to the negative 11 joules per operation. A biological synapse uses about 10 to the negative 15 joules per operation. 2025 memristor devices achieve about 10 to the negative 14 joules per operation, closing the gap significantly. That's roughly 1,000 times more energy efficient than conventional computing for neural network operations. Now let's discuss integration challenges. How do we combine these different nano devices into functional systems? Challenge 1 is interconnects. How do you wire together billions of nanoscale components? The solution is self-assembly using DNA programmed assembly. We encode the circuit design in DNA sequences that guide components to self-organize. Components tagged with complementary DNA sequences find each other and bind in the correct positions, forming circuits without manual placement. Challenge 2 is power delivery. Conventional wires don't work at the nanoscale. The solution is wireless power transfer using near-field electromagnetic coupling or even optical power transfer. Challenge 3 is heat dissipation. At high densities, even nanowatts per device add up to series heating. Total power equals number of devices times power per device. With 1 trillion devices each using 1 nanowatt, that's 1,000 watts to dissipate from a small chip. The solution is carbon nanotube thermal vias that conduct heat 10 times better than copper and integrate thermoelectric coolers at the nanoscale. Let's explore real-world applications in detail. Medical nanorobots are perhaps the most immediately impactful. Here's a nanorobot designed to clear arterial plaque. The red circle represents an artery. The blue dots are plaque deposits. The yellow circle is the nanorobot, and the green arrow shows its propulsion mechanism. How do nanorobots move inside the body? They use various propulsion mechanisms. Flagellar rotation driven by chemical fuel like glucose. Magnetic steering using external magnetic fields. Or ultrasonic propulsion, where sound waves provide thrust. Let's calculate the Reynolds number to understand the fluid dynamics at this scale. Reynolds number equals density times velocity times length, divided by viscosity. For a micron-sized robot moving at 10 micrometers per second in blood, that's 10 to the negative 5. This is extremely low Reynolds number flow. At such low Reynolds numbers, viscous forces completely dominate inertia. It's like swimming in molasses. Another application is environmental remediation, using catalytic nanoparticles that break down pollutants. Red dots represent pollutant molecules in contaminated water, and blue circles are catalytic nanoparticles that break them down into harmless products. Titanium dioxide nanoparticles can break down organic pollutants using just sunlight through photocatalysis. Titanium dioxide plus photon produces an electron and a hole. The hole oxidizes the pollutant, leading to degradation into carbon dioxide and water. The efficiency improves dramatically at the nanoscale because surface area to volume ratio increases, providing more active sites. Surface area per unit volume is proportional to 1 over radius. Comparing 10 nanometer particles to 1 millimeter particles, the surface area ratio is 100,000 to 1. We must address ethical and safety considerations. With great power comes great responsibility. Concern 1 is unintended environmental release. What happens if engineered nanodevices escape into ecosystems? Mitigation strategies include built-in kill switches that deactivate devices after a set time and materials designed to degrade into harmless products. Concern 2 is bioaccumulation. Could nanodevices accumulate in organisms and cause harm? We use biodegradable materials and design for rapid clearance from the body through kidneys or liver. Concern 3 is dual-use technology. Could medical nanorobots be weaponized? This requires international oversight similar to biological weapons conventions, with strict regulation of manufacturing capabilities. Let's look ahead to the next 5 years. What can we expect? 2026. We'll see the first clinical trials of therapeutic nanorobots for targeted drug delivery and cancer treatment. 2027. Commercial quantum computers using room temperature quantum dot qubits will become available. 2028. First consumer electronics using molecular transistors, achieving unprecedented computational density. 2029. Self-powered environmental sensor networks using energy harvesting nanodevices will blanket urban areas. 2030. Atomically precise manufacturing will transition from research labs to industrial production. The real power emerges from convergence, combining multiple nanodevice types into integrated systems. Imagine a system that combines quantum dot sensors for detection, DNA nanorobots for actuation, metamaterial cloaking for stealth, and energy harvesting for autonomy. This convergence enables capabilities impossible with any single technology. For example, an autonomous medical diagnostic system that circulates in your bloodstream continuously. Quantum dots detect disease biomarkers with single-molecule sensitivity. Neuromorphic processors analyze patterns in real time using learned models. DNA nanorobots deliver therapeutic cargo precisely when and where needed. Energy harvesting devices power the entire system using body heat. And metamaterial antennas enable wireless communication to external monitoring systems. Despite remarkable progress, significant challenges remain. Challenge 1 is scalable manufacturing, moving from lab scale to mass production while maintaining atomic precision. Challenge 2 is long-term stability. Nanodevices must function reliably for years, not just hours. Challenge 3 is managing the complexity of systems with trillions of interacting components. And Challenge 4 is developing appropriate regulatory frameworks that ensure safety without stifling innovation. Let me summarize what we've covered in this lecture. We can now build devices atom by atom with sub-angstrom precision, using atomically precise manufacturing. Quantum coherence at room temperature enables practical quantum computing with quantum dot arrays. DNA nanorobots can autonomously sense their environment, make decisions, and execute actions. Metamaterials give us electromagnetic properties impossible to find in natural materials. Energy harvesting from ambient sources enables truly autonomous nanodevices. Neuromorphic devices bring brain-like efficiency to artificial intelligence hardware. The convergence of these technologies will fundamentally transform medicine, computing, energy systems, and environmental management. We stand at the threshold of a new technological era. The ability to manipulate matter at the atomic scale, combined with our growing understanding of quantum mechanics, biological systems, and emergent phenomena, gives us unprecedented power to engineer our world. The next generation of nanodevices will blur the boundaries between living and non-living, between natural and artificial, opening possibilities we're only beginning to imagine. Thank you for your attention.